Welcome to Spring LIB.
Okay, in this problem we have a Compton scattering event where an incoming photon scatters from an electron at mass and is deflected at a 90-degree angle. The lambda, the wavelength of our photon, is 4.5 picometers, e to the negative 12 meters. We're asked to find a number of things. We're asked to find the kinetic energy of the electron after the scattering, how this kinetic energy compares to its rest energy, mc squared. We're asked for the velocity of the electron, the momentum of the electron, and momentum relative to its non-relativistic value. So this is heavily implying that the scattered electron is going to have relativistic velocity. So we'll have to be careful there. We're going to use the Compton scattering equation, which relates the change in wavelength to a scattering angle. We're going to need to know the energy of a photon as it's related to its wavelength. And we're going to need to know the relativistic momentum, which involves the Lorentz factor gamma, which we define here. It's related to the velocity of the object. We'll be using Planck's constant, speed of light, and the mass of an electron. So let's jump into it. So to start out, we need to find the kinetic energy of the electron. We need to know the change in wavelength of the photon in the scattering. So we can start by using the Compton scattering equation. Y prime equals, or lambda prime equals lambda plus h over mc, 1 minus cosine of 90 degrees, because the photon is scattered 90 degrees as per the problem. So we find, since 90 degrees is 0, this is really just lambda plus h over mc. H over mc is called the Compton wavelength, and we know it's useful to perhaps have its value recorded because it's used frequently. So plugging in our value for the initial wavelength of our light plus our Compton wavelength, which is about 2.426 picometers. I think I am using the wrong wavelength. That's right. I used the wrong wavelength here. 4.5 e to the negative 12 plus about 2.4 e to the negative 12 gives us a result of about 6.926 picometers. So this is the new wavelength of our light. So now that we know this new wavelength, we can set up conservation of energy. So initially, the photon is coming out of a rest electron, so it'll have an energy of hc over lambda. After the scattering, this photon will have a new lambda, so a new energy. And the photon, or the electron rather, will have a kinetic energy, some kinetic energy k. We can solve for k by simply getting the change in the photon energy. Make it as easy as possible. Now we can simply plug in our two different wavelengths, the initial and the final we calculated, and we'll get a result of 1.536 times 10 to the negative 14 joules. And if you're curious, this is about 96,000 electron volts, or 96 keV. But we don't need to use it in electron volts. So now that we have the kinetic energy, we can compare it to its rest energy. Well, first let's box this because it's something we're looking to solve for. So that as a ratio, we can say, comparing it to its rest energy, we have 1.5 e to the negative 14 joules compared to mc, which is, well, mc squared rather, 9.1 e to the negative 31 kilograms times the speed of light, which is 3 times 10 to the 8 meters per second. And after performing this computation, we get a result of 0.187. So this electron is at about 20% the kinetic energy of light, which is pretty considerable. So this is something we need to be looking out for in the rest of the problem, that this definitely is a relativistic electron. So let's look at the next part of this problem. We're asked to find the actual velocity, and I'm going to venture a guess that this velocity is going to be comparable to the speed of light. So using, well, let's back up a bit. Using just a simple kinetic energy, 1/2 mv squared, we can solve for v to be root 2 times k over m. We can plug in our value for k and the mass of an electron, and we will get a speed of 1.87 times 10 to the 8 meters per second. So comparing that to the speed of light, which is 3 times 10 to the 8 meters per second, you can see this is a very considerable fraction of the speed of light, as I suspected. Let's get an actual gamma factor for it. It's the 1.87 e to the 8 squared over the 3 e to the 8 squared. These are both in meters per second. We get a resulting gamma factor of 1.265. Recall the momentum, the relativistic momentum of a particle is gamma mv. So we can take all of our results, combine them. We'll use the mass of the electron and the velocity, 1.87 e to the 8 meters per second. And this will give us a result of 2.11 e to the negative 22 kilogram meters per second. And if you're wondering why is this momentum so small, it's because we're dealing with a single electron. So this electron mass we can plug it in, 9.1 e to the negative 31 kilograms. So even if the velocity is enormous, the mass is so small that this momentum is going to be pretty small. But when we actually compare this to the non-relativistic momentum, just mv, we get a result. We can simply, just by the definition of relativistic momentum versus normal momentum, you can see that the ratio is going to be gamma, which is going to be 1.265. So that's everything we're asked to find. In order to produce a 90-degree scattering of a photon or at least when it's hitting an electron in a Compton scattering situation, you're going to have a resulting electron velocity that's comparable to the speed of light. That's a significant fraction of it. So that's a somewhat interesting result. Thank you very much.